Let's have a look now at cubics, and we've had a bit of a look at these already this year. And they're known as a power function, like the quadratics. Power functions are in the form x to the power of n, and cubics graphs in the form x to the power of 3. It's the cubic function. And the key to these positive cubics and negative cubics, ones we're going to look at, is this point here called the point of inflection. And at that point, the gradient, at that precise point, the gradient equals 0, the graph flattens out. I think I've mentioned before, I get a bit lazy when I draw mine, and you probably sometimes can't tell that it flattens out, but anyway, there it is. So that's the type of graph we're looking at here. Now we've got our dilations again, and similar pattern to last time. Okay, you can see there that the green graph is 2x cubed, so it's moved away from the x-axis. And because of the 2 there in front of the x cubed in the green graph, it's been dilated by a factor of 2 from the x-axis. Okay, so dilated by a factor of 2 from the x-axis for y equals 2x cubed. And why is that? Okay, well, if you had y equals x cubed and x was equal 1, so y would equal 1 cubed. So y would equal 1. So a point on the purple graph will be 1, 1. Now if you've got 2x cubed, that's 2 times 1 cubed, that equals 2. So if it's 2x cubed, you've got the point 1, 2. So you've got 1, 1 on the purple graph, and 1, 2 would be on the green graph. So every x value is getting doubled. Okay, now third graph there is y equals a half x cubed. Okay, and that will dilate the graph by a factor of a half from the x-axis, which effectively, as you can see, takes it closer to the x-axis. Alright, reflections. If you get negative x cubed, like that, we call it a negative cubic. So the purple one is a positive cubic, our negative cubic slants the other way. It's a reflection in the x-axis. So in other words, points from here are taken down to here, reflected. Similarly as before, 1, 1 down here will become 1, negative 1. Now here you can also get reflections in the y-axis. You'll notice here I've got the graph in purple of y equals x minus 1 cubed. Now if we had a graph of y equals negative x minus 1 cubed, let's look at what would happen in that situation. With the negative inside the bracket there, the graph actually gets reflected in the y-axis. And you can see there, if x is 1 here, we're going to get y equals 1 minus 1 cubed, which is 0. Over here, if x equals 1, if x equals negative 1, we get negative 1 minus 1 cubed, which is also 0. So hence you get negative 1, 0 here and 1, 0 here. So in this situation, points over here are reflected over here. So they're reflected on the other side of the y-axis. So that's the effect of a negative inside the bracket there. It's called a reflection in the y-axis. Translations, same as before. If we've got a negative 3 inside our bracket, the graph is translated 3 units to the right. And if you get a plus 3 inside our bracket, x plus 3 cubed, graph is translated 3 units to the left. Our translations, okay, we've got a cubic function here, and it's been translated 3 units down, x cubed minus 3. And so we get our combination of transformations here. That's our dilation factor again. Okay, so dilation factor. And of course, if a is negative, we get a negative cubic going the other way. Like that. left-right shift. So a negative takes us to the right, a positive takes us to the left. Up-down shift, positive up, negative down. Okay, so let's look at this first question here. State the necessary changes to transform the graph y equals x cubed. Right, so we've got the equation here, so the 2 in front of the bracket there, so the graph is dilated by a factor of 2 from the x-axis. Notice in the book sometimes they also say, you can also say that's dilated by a factor of 2 in the direction of the y-axis. Okay, but I prefer us just to keep it from the x-axis at the moment. There's no reflections, so we look at left and right translations. The graph is translated 1 unit to the left. And finally, we've got a negative 4 there. So the graph is translated four units down. So dilations, left-right translations, up-down translations, or vertical translations. Okay, next one. First thing we have to do is look at the coordinates of the stationary point of inflection for this graph. Y equals negative outside of x plus 3 cubed. Okay, what's the negative going to do? Well, that's going to make it a negative cubic in a moment, so we'll just keep an eye on that. But the plus 3 will take the graph 3 units to the left. Okay, so our x coordinate of our point of inflection is going to be negative 3 if we take it 3 units to the left, and the minus 1 there takes it down 1 place, so our stationary point of inflection will be negative 3, negative 1, because that takes it left 3 places, that takes it down one place. Next thing we've asked to find here are the X and Y intercept. Okay, so to find the Y intercept we make x equals 0. And if we do that, negative outside of 0 plus 3 cubed minus 1. So that's going to be negative 27 take 1 equals negative 28. So that's our y-intercept, 0, negative 28. X-intercept, we make y equals 0, so 0 equals negative outside of x plus 3 cubed minus 1. A good step to do here straight away is to take the negative x plus 3 cubed over to the left-hand side, and make it a positive x plus 3 cubed equals negative 1. Then we can get the cube root of both sides. So x plus 3 is the cube root of x plus 3 cubed equals the cube root of negative 1, which is just negative 1. So x plus 3 equals negative 1. X will equal negative 4. So there's our x-intercept, negative 4, 0. Let's have a go now at drawing the graph. Okay, so I've drawn the graph now. We've got our x-intercept at negative 4, our point of inflection there at negative 3, negative 1. Our y-intercept is way down here at negative 27, so I haven't bothered to draw that because I wanted to draw it to scale as much as possible, and 0, neg 27 is going to be a fair way south of there, so it's down there. But anyway, there's the graph of negative x plus 3 cubed take 1. And what have we done to this graph? Well, there's been no dilations, there's no number in front of the bracket there. So we've reflected. Remember, this is what we're doing to the, just to put you in the picture here, our standard cubic graph. Okay, what have we done to that to create this? Okay, so we've reflected in the x-axis. As you can see, it's got that negative cubic shape, sloping the other way. Horizontal translation. And that was 3 units to the left. And vertical translation 1 unit down. Okay, so that's what we've done to that original graph of y equals x cubed, this one here, to create our graph of negative x plus 3 cubed take 1. Harder type of cubic graph now, and what I'm going to do this time is just perhaps just draw a quick sketch of what this one might look at, might look like, just to get a bit of a picture of it. So I've just drawn up some axes there, but these minus x ones can be a little bit tricky. So I'll show you what I do with them, and use this method if you wish. Okay, so what I do with them is I like to make this, first of all, negative x plus 4 cubed, and that's the same thing, remember. 4 take x is the same as negative x take 4. And then I like to create a square bracket here, and then take a negative outside, like so. Plus 6. Now in doing that, what it reminds me is that when I'm looking at my my point of inflection, I'm going to the right 4 places and up 6 places. Now there's a shortcut here. You can remember after a while that in 4 minus x situations, your point of inflection is 4, not neg 4, and 6. But when I see that neg 4, aha, I know I'm going to the right 4 units and then up 6 units. So my point of inflection is going to be here at 4, 6. Okay. So that's a good starting point to look at that. And also with these 4 minus x questions, you'll find that they end up being a negative cubic type situation. So ones that are shaped this way. So rough sketch first up of what it's going to look like, and my point of inflection, stationary point of inflection, stationary point of inflection is 4, 6. Now let's look at the x-intercept and the y-intercept. Okay, just divide the screen in 2 here. And find out the x-intercept on this side and the y-intercept on this side. X-intercept, make y equal 0, so we get 0 equals 4 minus x cubed plus 6. So that means 4 minus x cubed equals negative 6 if we take that guy to the other side. Therefore the cube root of both sides, so 4 minus x, equals the cube root of negative 6. At which stage you'll have to look at your calculator. But just to keep on going a step further, that means 4 minus the cube root of negative 6 equals x. And to get that, I've taken that one to that side and that one to that side. So 4 minus cube root of neg 6, x equals 5.8. X equals 5.8. So the x-intercept is 5.8, 0. Y-intercept make x equal 0. So y equals 4 cubed plus 6. Y equals 70. So quite a high y-intercept. Okay, last slide. We've got 4, 6 as our point of inflection. 5.8 as our x-intercept. Our y-intercept, okay, was 70. Once again, in the interest of drawing this to scale, I'm not going to draw the graph way up to 70, but that's where it would cross the y-axis. Let's look at what transformations have occurred. First of all, there's no dilations. There's no number in front of the bracket there. The graph is reflected in the y-axis. That's due to that negative x inside the bracket. Okay, the negative is outside the bracket, reflecting in the x-axis. The negative is inside the bracket, reflecting in the y-axis. Horizontal translation, 4 units to the right. Okay, so 4 units that way. That's why I've got our point of inflection as 4, 6, and we've got our vertical translation 6 units up. Having trouble here today. It's a little bit humid, so things are a bit sticky. Vertical translation 6 units up. So there we go. There's one of our cubic graphs. Right, some questions now to do, and I'll put those in the next slide. Here's our questions here for exercise 2b. It's on page 68. Number 9, I haven't done an example here, but it's finding the equation given a graph. Okay, so for example, I might just do a quick example on the next page now I think about it. So let's have a look at this graph here. If we've got, so we've got this graph here, and it looks something like this. Start again. And point of inflection here at 1, 2. We have to find the equation of it. So we know its general form is going to be y equals a outside of x minus 1 squared plus 2. How do we know that? Because it's gone across 1 unit and up 2 units. Also, it's passing through 0, 0. Notice that as well. So we can use either one of those points and suggest that you use 0, 0 by substituting in 0 for y and 0 for x, and then finding a. So same sort of strategy. Each time you've got to find an equation that come up in exams, get the general formula, then you need to find that coefficient and use one of the points to do so. Alright, that's all for now.